This is our second lesson on electrostatics for Physical Sciences grade 10. Two different charges, a negative and a positive, will exert a force on each other. This force is called an electrostatic force. For an example, if you have a positive and a negative charge next to each other, they will attract. The negative charge exerts an attractive force on the positive charge, and the positive charge in turn exerts an attractive force on the negative charge. However, if you have a negative and a negative charge, they experience a force of repulsion. This means that they push each other away. The negative charge exerts a repulsive force on the negative charge, and the other negative charge exerts a repulsive force on the other negative charge. Similarly, if you have a positive and a positive charge, they experience a force of repulsion, so they push each other away. The positive charge exerts a repulsive force on the positive charge, and the other positive charge exerts a repulsive force on the other positive charge. The closer together the charges are, the stronger the electrostatic force between them. At the end of this lesson, you will be able to state that like charges repel and opposite charges attract. State the SI unit for electric charge. Apply the principle of conservation of charge using charges of identical size. State the principle of charge quantization and apply this principle. Materials can be a conductor or an insulator. Conductors allow a flow of charge through them. If an excess charge is placed on a conductor, the like charges will repel each other and spread out over the outside surface of the object. Electrons are free to move in conductors. Insulators do not allow a flow of charge through them. Electrons do not move in insulators. If an excess charge is placed on an insulator, it will stay where it is put, and there will be a concentration of charge in that area of the object. Examples of conductors are mainly gold, steel, copper. And examples of insulators are materials such as rubber, glass, or oil. The symbol for charge is Q, and its SI unit is coulombs, or capital letter C. When two conductors are made to touch, the total charge on them is shared between the two conductors. If two conductors are identical, then each conductor will be left with half of the total net charge. This is in accordance with the principle of conservation of charge that states that the net charge on an isolated system remains constant during any physical process. Let's consider two identical conducting spheres, sphere 1 and sphere 2, on insulating stands. The sphere is a conductor, meaning it allows negative charge or electrons to flow freely. The stand which the sphere stands on, or the sphere is placed on, is an insulator, meaning it does not allow free electron movement or free negative charge movement. The two spheres are allowed to touch, and they will share the charge. If the initial charge on sphere 1 is Q1 and the initial charge on sphere 2 is Q2, then the final charge on the two spheres after they've been brought into contact is Q equals to Q1 plus Q2 divided by 2. When a positive conductor touches an identical neutral conductor, electrons are transferred to make the charges equal. Be mindful it is the negative charge electrons which are transferred. If a positive conductor, sphere 1, touches a neutral conductor, sphere 2, negative charges which are carried by electrons are transferred from the neutral conductor to the positive conductor. This means that 1.4 coulombs of negative charge is transferred from sphere 2 to sphere 1, or from conductor 1 or from conductor 2 to conductor 1. Negative charge or electrons move from the sphere which is more negative to the sphere which is more positive. Sphere 1 is more positive than sphere 2. When conductors are separated after touching, they will have an equal amount of positive charge, which will be equals to 1.4 coulombs. The new charge is determined by adding the initial charge of sphere 1, which is 2.8, plus the initial charge on sphere 2, which is 0, all divided by 2, which will give us positive 1.4 coulombs. So now, after touching, the spheres will each have a charge of 1.4 coulombs, which is positive. When a negative conductor touches an identical neutral conductor, electrons are transferred to make the charges equal. A negative conductor, sphere 1, touches a neutral conductor, sphere 2. Negative charges or electrons are transferred from sphere 1 to sphere 2. This means that 1.4 coulombs of negative charge is transferred from the negatively charged sphere 1 to the electrically neutral sphere 2. Negative charge or electrons always move from the more negative sphere to the more positive sphere. Sphere 1 is more negative than sphere 2, so electrons move from sphere 1 to sphere 2. At the end, both conductors or both spheres will have an equal positive charge of minus 1.4 coulombs. To determine the new charge on each sphere after touching, we will say that Q is equals to the initial charge on sphere 1, which is negative 2.8, plus the initial charge on sphere 2, which is 0, and all divided by 2. This will equal negative 1.4 coulombs. This means that the new charge or the final charge on the two spheres is equal, and it will be negative 1.4 coulombs. The charge on a single electron is given by QE, which is equals to negative 1.6 multiplied by 10 raised to the power of minus 19 coulombs. This value is positive for protons, meaning the charge on a single proton is equals to 1.6 multiplied by 10 raised to the power of minus 19 coulombs. And you will see how it is positive for protons in the next problem that we will solve together. Now, the important thing is that all other charges in the universe, all of them, consists or are made up of an integer multiple of this charge of QE, and this is known as charge quantization, whereby it is given by Q equals to big letter Q is equals to N times small letter q e. This means all charges in the universe consist of an integer multiple of the charge on one electron eq. This means that all the other charges are either 1.6 multiplied by 10 raised to the power of minus 19 coulombs, or 2 times 1.6 multiplied by 10 raised to the power of minus 19 coulombs, or 3 times 1.6 multiplied by 10 raised to the power of minus 19 coulombs, or 4 times 1.6 multiplied by 10 raised to the power of minus 19 coulombs, or 5 times 1.6 multiplied by 10 raised to the power of minus 19 coulombs, and on and on and on. That's why we say it is an integer multiple, so that n is for either 1, 2, 3, 4, 5, 6, 7, 8, and it denotes the number of electrons or the number of protons. If this is not making sense, in the next problem you will see what I mean. Now, Q is the charge on the object, and N is the number of electrons or protons, and QE is the charge on a single electron or proton. In electrostatics, we often work with charges in microcoulombs, or 1 multiplied by 10 raised to the power of minus 6 coulombs. Micro means 10 raised to the power of minus 6, or sometimes we work with nanocoulombs, where it is 1 multiplied by 10 raised to the power of minus 9. Nano means 10 raised to the power of minus 9. So it is important for you to know these conversions. Like I said, micro means 10 raised to the power of negative 6, and nano means 10 raised to the power of negative 9 or minus 9. Two identical metal spheres on insulating stands have different charges. Sphere 1 has a charge of minus 9.6 multiplied by 10 raised to the power of minus 18 coulombs. Sphere 2 has 60 excess protons. If the two spheres are brought together or are brought into contact and then separated, what charge will each sphere have? That is the question that we need to solve. So we have sphere 1 and sphere 2. Sphere 1 has a negative charge of 9.6 multiplied by 10 raised to the power of minus 18 coulombs. This means that it has an excess of electrons. Sphere 2 has an excess of 60 protons, meaning it has a deficiency of electrons. This means it is positively charged. However, we do not know the charge on sphere 2 in coulombs, and that's what we need to first determine. And to do so, we must determine the total charge when given a certain number of protons. We know that charge is quantized, and that means that a proton has a charge of 1.6 multiplied by 10 raised to the power of minus 19 coulombs. So if we have the number of protons n, which is 60, we can just simply multiply it by 1.6 multiplied by 10 raised to the power of minus 19 coulombs, because that is the charge on a single proton that we previously talked about. And if you put this in your calculator, you will find that the charge on sphere 2 is equals to 9.6 or positive 9.6 multiplied by 10 raised to the power of minus 18 coulombs. But the charge on sphere 1 is equals to negative 9.6 multiplied by 10 raised to the power of minus 18 coulombs. And the charge on sphere 2 is positive 9.6 multiplied by 10 raised to the power of minus 18 coulombs. When these two oppositely charged identical spheres touch, they will have the same charge when separated. So after touching and we separate them, they will both have the same charge. Negative charge or electrons will be transferred from the more negative sphere 1 to the more positive sphere 2. This means that there will be a charge transfer of negative minus 9.6 multiplied by 10 raised to the power of minus 18 coulombs. The new charge Q will be equal to the initial charge on sphere 1, which is negative 9.6 multiplied by 10 raised to the power of minus 18, plus the initial charge on sphere 2, which is positive 9.6 multiplied by 10 raised to the power of minus 18, all of it divided by 2. So if you put these two values on a calculator, we will find that the new charge on each sphere after touching, when we separate them, is equals to 0 coulombs. So it means both spheres after touching will actually now be neutral, because each of them will have a charge of 0 coulombs. Sphere 1 and sphere 2 will have a charge of 0 coulombs or 0 C. We have come to the end of our lesson, and we have learned that opposite charges attract, like charges repel, and that conductors allow negative charge or electrons to flow while insulators do not. The symbol for charge is capital letter Q, and the SI unit is coulombs or C. And when two identical conducting spheres touch, negative charge is transferred from the more negative sphere to the more positive sphere. And the new charge, the final charge on each sphere after touching, will be given by Q equals to Q1 plus Q2 divided by 2. The charge on a single electron is given by minus 1.6 multiplied by 10 raised to the power of minus 19 coulombs, and this value is positive for protons. It's the same value, just that if you are working with protons, you have to indicate that it is positive. Also learned that charge is quantized, meaning all other charge in the universe is just an integer multiple of this QE value, or of this charge on a single electron or a single proton. Thank you so much for watching.